public API of ActionKV is comprised of 4 operations: get, delete, insert, and update. Table 7.6 describes these operations. Naming is difficult. To access stored key value pairs, should the API provide a get, retrieve, or perhaps fetch? Should setting values be insert, store, or set? ActionKV attempts to stay neutral by deferring these decisions to the API provided by STD Collections HashMap. The following listing, an excerpt from listing 7.8, shows the naming considerations mentioned in the preceding sidebar. For our project, we use Rust's matching facilities to efficiently work with the command line arguments and to dispatch to the correct internal function. In full, listing 7.8 presents the code for ActionKV version 1. Notice that the heavy lifting of interacting with the file system is delegated to an instance of ActionKV called store. How ActionKV operates is explained in section 7.7. The source for this listing is in ch7/ch7-akv1/src/akv_mem.rs. Section 7.6.1. Tailoring what is compiled with conditional compilation. Rust provides excellent facilities for altering what is compiled depending on the compiler target architecture. Generally, this is the target's OS, but can be facilities provided by its CPU. Changing what is compiled depending on some compile time condition is known as conditional compilation. To add conditional compilation to your project, annotate your source code with CFG attributes. CFG works in conjunction with the target parameter provided to Rust-C during compilation. Listing 7.8 provides a usage string common as quick documentation for command line utilities for multiple operating systems. It's replicated in the following listing, which uses conditional compilation to provide 2 definitions of const usage in the code. When the project is built for Windows, the usage string contains a .exe file extension. The resulting binary files include only the data that is relevant for their target. There is no negation operator for these matches. That is, this expression does not work. Instead, there is a function-like syntax for specifying matches. Use #CFG of not surrounded in square brackets for negation. #CFG of all surrounded in square brackets and #CFG of any surrounded in square brackets are also available to match elements of a list. Lastly, it's possible to tweak CFG attributes when invoking cargo or Rust-C via the --CFG attribute command line argument. The list of conditions that can trigger compilation changes is extensive. Table 7.7 outlines several of these. Section 7.7. Understanding the core of ActionKV, the lib ActionKV crate. The command line application built in section 7.6 dispatches its work to lib ActionKV, ActionKV. The responsibilities of the ActionKV struct are to manage interactions with the file system and to encode and decode data from the on-disk format. Figure 7.2 depicts the relationships. Section 7.7.1. Initializing the ActionKV struct. Listing 7.10, an excerpt from listing 7.8, shows the initialization process of lib ActionKV, ActionKV. To create an instance of lib ActionKV, ActionKV, we need to do the following. 1. Point to the file where the data is stored. 2. Load an in-memory index from the data within the file. Both steps return result, which is why calls to .expect are also present. Let's now look inside the code of ActionKV open and ActionKV load. Open opens the file from disk and load loads the offsets of any pre-existing data into an in-memory index. The code uses two type aliases, byte str and byte string. We'll use the byte str type alias for data that tends to be used as a string but happens to be in binary or raw bytes format. Its text-based peer is the built-in str. Unlike str, byte str is not guaranteed to contain valid UTF-8 text. Both str and U8 surrounded in square brackets, or its alias byte str, are seen in the wild as &str and &U8 surrounded in square brackets, or &byte str. Both of these are called slices. The alias byte string will be the workhorse when we want to use a type that behaves like a string. It's also one that can contain arbitrary binary data. The following listing, an excerpt from listing 7.16, demonstrates the use of ActionKV open. What is EOF? File operations in Rust might return an error of type stdio, error kind, unexpected EOF. But what is EOF? The end of file, or EOF, is a convention that operating systems provide to applications. There is no special marker or delimiter at the end of a file within the file itself. EOF is a 0 byte, 0U8. When reading from a file, the OS tells the application how many bytes were successfully read from storage. If no bytes were successfully read from disk, yet no error condition was detected, then the OS, and therefore the application, assume that EOF has been reached. This works because the OS has the responsibility for interacting with physical devices. When a file is read by an application, the application notifies the OS that it would like to access the disk. Section 7.7.2. Processing an individual record. ActionKV uses a published standard for its on-disk representation. It is an implementation of the BitCask storage backend that was developed for the original implementation of the REAC database. BitCask belongs to a family of file formats known in the literature as log-structured hash tables. What is REAC? REAC, a NoSQL database, was developed during the height of the NoSQL movement and competed against similar systems such as MongoDB, Apache CouchDB, and Tokyo Tyrant. It distinguished itself with its emphasis on resilience to failure. Although it was slower than its peers, it guaranteed that it never lost data. That guarantee was enabled in part because of its smart choice of a data format. BitCask lays every record in a prescribed manner. Figure 7.3 illustrates a single record in the BitCask file format. Every key-value pair is prefixed by 12 bytes. Those bytes describe its length, key_len plus val_len, and its content, checksum. The process_record function does the processing for this within ActionKV. It begins by reading 12 bytes that represent three integers, a checksum, the length of the key, and the length of the value. Those values are then used to read the rest of the data from disk and verify what's intended. The following listing, an extract from listing 7.16, shows the code for this process. Section 7.7.3. Writing multi-byte binary data to disk in a guaranteed byte order. One challenge that our code faces is that it needs to be able to store multi-byte data to disk in a deterministic way. This sounds easy, but computing platforms differ as to how numbers are read. Some read the 4 bytes of an I-32 from left to right. Others read from right to left. That could potentially be a problem if the program is designed to be written by one computer and loaded by another. The Rust ecosystem provides some support here. The byte order crate can extend types that implement the standard libraries stdio read and stdio write traits. stdio read and stdio write are commonly associated with the stdio file, but are also implemented by other types such as U8 surrounded in square brackets and TCP stream. The extensions can guarantee how multi-byte sequences are interpreted, either as Little Endian or Big Endian. To follow what's going on with our key value store, it will help to have an understanding of how byte order works. Listing 7.14 is a toy application that demonstrates the core functionality. Lines 11 through 23 show how to write to a file, and lines 28 through 35 show how to read from one. The two key lines are byte order, Little Endian, and its peers, Big Endian and Native Endian, not used in listing 7.14, are types that declare how multi-byte data is written to and read from disk. Byte order, read bytes ext, and byte order, write bytes ext are traits. In some sense, these are invisible within the code. These extend methods to primitive types such as F32 and I16 without further ceremony. Bringing those into scope with a use statement immediately adds powers to the types that are implemented within the source of byte order. In practice, that means primitive types. Rust, as a statically typed language, makes this transformation at compile time. From the running program's point of view, integers always have the ability to write themselves to disk in a predefined order. When executed, listing 7.14 produces a visualization of the byte patterns that are created by writing 1_U32, 2_I8, and 3.0_F32 in Little Endian order. Here's the output. The following listing shows the metadata for the project in listing 7.14. You'll find the source code for the following listing in this file. The source code for listing 7.14 is in this file. Section 7.7.4. Validating I/O errors with checksums. Action KB version 1 has no method of validating what it has read from disk is what was written to disk. What if something is interrupted during the original write? We may not be able to recover the original data if this is the case, but if we could recognize the issue, then we would be in a position to alert the user. A well-worn path to overcome this problem is to use a technique called a checksum. Here is how it works. Saving to disk. Before data is written to disk, a checking function, there are many options as to which function, is applied to those bytes. The result of the checking function, the checksum, is written alongside the original data. No checksum is calculated for the bytes of the checksum. If something breaks while writing the checksum's own bytes to disk, this will be noticed later as an error. Reading from disk. Read the data and the saved checksum, applying the checking function to the data. Then compare the results of the two checking functions. If the two results do not match, an error has occurred, and the data should be considered corrupt. Which checking function should you use? Like many things in computer science, it depends. An ideal checksum function would return the same result for the same input. Always return a different result for different inputs. Be fast. Be easy to implement. Table 7.8 compares the different checksum approaches. To summarize, the parity bit is easy and fast, but it is somewhat prone to error. CRC32, cyclic redundancy check returning 32 bits, is much more complex, but its results are more trustworthy. Cryptographic hash functions are more complex still, although being significantly slower, they provide a higher level of assurance. Functions that you might see in the wild depend on your application domain. More traditional areas might see the use of simpler systems, such as parity bit or CRC32. Implementing parity bit checking. This section describes one of the simpler checksum schemes, parity checking. Parity checks count the number of ones within a bit stream. These store a bit that indicates whether the count was even or odd. Parity bits are traditionally used for error detection within noisy communication systems, such as transmitting data over analog systems such as radio waves. For example, the ASCII encoding of text has a particular property that makes it quite convenient for this scheme. Its 128 characters only require 7 bits of storage. 128 equals 2 to the 7th. That leaves 1 spare bit in every byte. Systems can also include parity bits in larger streams of bytes. Listing 7.15 presents an overly chatty implementation. The parity_bit function in lines 1 through 10 takes an arbitrary stream of bytes and returns a U8, indicating whether the count of the input's bits was even or odd. When executed, listing 7.15 produces the following output. Note: the code for the following listing is in ch7/ch7-parity_bit/src/main.rs. Section 7.7.5. Inserting a new key-value pair into an existing database. As discussed in Section 7.6, there are 4 operations that our code needs to support: insert, get, update, and delete. Because we're using an append-only design, this means that the last 2 operations can be implemented as variants of insert. You may have noticed that during load, the inner loop continues until the end of the file. This allows more recent updates to overwrite stale data, including deletions. Inserting a record is almost the inverse of process_record, described in Section 7.7.2. For example, Section 7.7.6, the full code listing for ActionKV. lib_ActionKV performs the heavy listing in our key value stores. You have already explored much of the ActionKV project throughout Section 7.7. The following listing, which you'll find in the file ch7/ch7-actionkv1/src/lib.rs, presents the project code in full. If you've made it this far, you should congratulate yourself. You've implemented a key value store that will happily store and retrieve whatever you have to throw at it. Section 7.7.7. Working with keys and values with hash map and B-tree map. Working with key value pairs happens in almost every programming language. For the tremendous benefit of learners everywhere, this task and the data structures that support it have many names. You might have encountered someone with a computer science background who prefers to use the term hash table. Perl and Ruby call these hashes. Lua does the opposite and uses the term table. Many communities name the structure after a metaphor, such as a dictionary or a map. Other communities prefer naming based on the role that the structure plays. PHP describes these as associative arrays. JavaScript's objects tend to be implemented as key-value pair collections, and so the generic term object suffices. Static languages tend to name these according to how they are implemented. C++ and Java distinguish between a hash map and a tree map. Rust uses the term hash map and B-tree map to define 2 implementations of the same abstract type. Rust is closest to C++ and Java in this regard. In this book, the term collection of key-value pairs and associative array refer to the abstract data type. Hash table refers to associative arrays implemented with a hash table, and hash map refers to Rust's implementation of hash tables. What is a hash? What is hashing? If you've ever been confused by the term hash, it may help to understand that this relates to an implementation decision made to enable non-integer keys to map to values. Hopefully, the following definitions will clarify the term. A hash map is implemented with a hash function. Computer scientists will understand that this implies a certain behavior pattern in common cases. A hash map has a constant time lookup in general, formally denoted as O of 1 in big O notation, although a hash map's performance can suffer when its underlying hash function encounters some pathologic cases, as we'll see shortly. A hash function maps between values of variable length to fixed length. In practice, the return value of a hash function is an integer. That fixed width value can then be used to build an efficient lookup table. This internal lookup table is known as a hash table. The following example shows a basic hash function for $str that simply interprets the first character of a string as an unsigned integer. It, therefore, uses the first character of the string as a hash value. Basic_hash can take any string as input, an infinite set of possible inputs, and return a fixed width result for all those in a deterministic manner. That's great, but although basic_hash is fast, it has some significant faults. If multiple inputs start with the same character, for example, Tonga and Tuvalu, these result in the same output. This happens in every instance when an infinite input space is mapped into a finite space, but it's particularly bad here. Natural language text is not uniformly distributed. Hash tables, including Rust's hash map, deal with this phenomenon, which is called a hash collision. These provide a backup location for keys with the same hash values. That secondary storage is typically a vec of T that we'll call the collision store. When collisions occur, the collision store is scanned from front to back when it is accessed. That linear scan takes longer and longer to run as the store's size increases. Attackers can make use of this characteristic to overload the computer that's performing the hash function. In general terms, faster hash functions do less work to avoid being attacked. These will also perform best when their inputs are within a defined range. Fully understanding the internals of how hash tables are implemented is too much to detail for this sidebar, but it's a fascinating topic for programmers who want to extract optimum performance and memory usage from their programs. Section 7.7.8. Creating a hash map and populating it with values. The next listing provides a collection of key value pairs encoded as JSON. It uses some Polynesian island nations and their capital cities to show the use of an associative array. Rust does not provide a literal syntax for hash map within the standard library. To insert items and get them out again, follow the example provided in listing 7.18, whose source is available in ch7/ch7-pacific-basic/src/main.rs. When executed, listing 7.18 produces the following line in the console. Writing everything out as method calls can feel needlessly verbose at times. With some support from the wider Rust ecosystem, it's possible to inject JSON string literals into Rust code. It's best that the conversion is done at compile time, meaning no loss of runtime performance. The output of listing 7.19 is also a single line. The next listing uses a SERD JSON crate to include JSON literals within your Rust source code. Its source is in the ch7/ch7-pacific-json/src/main.rs file. Section 7.7.9. Retrieving values from hash map and B-tree map. The main advantage that a key value store provides is its ability to access its values. There are two ways to achieve this. To demonstrate, let's assume that we have initialized capitals from listing 7.19. The approach, already demonstrated, is to access values via square brackets. This approach returns a read-only reference to the value, which is deceptive when dealing with examples containing string literals because their status as references is somewhat disguised. In the syntax used by Rust's documentation, this is described as $V, where ampersand denotes a read-only reference and V is the type of the value. If the key is not present, the program will panic. Note: index notation is supported by all types that implement the index trait. Accessing capitals, Tonga surrounded in double quotes and then surrounded by square brackets, is syntactic sugar for capitals.index of Tonga surrounded in quotes. It's also possible to use the .get method on hashmap. This returns an option of $V, providing the opportunity to recover from cases where values are missing. For example, other important operations supported by hashmap include deleting key value pairs with the .remove method, iterating over keys, values, and key value pairs with the .keys, .values, and .iter methods respectively, as well as their read-write variants, .keys_mute, .values_mute, and .iter_mute. There is no method for iterating through a subset of the data. For that, we need to use btree map. Section 7.7.10. How to decide between hashmap and btree map. If you're wondering about which backing data structure to choose, here is a simple guideline. Use hashmap unless you have a good reason to use btree map. btree map is faster when there's a natural ordering between the keys, and your application makes use of that arrangement. Table 7.9 highlights the differences. Let's demonstrate these two use cases with a small example from Europe. The Dutch East India Company, known as VOC after the initials of its Dutch name, Verenigde Oostindische Company, was an extremely powerful economic and political force at its peak. For 2 centuries, VOC was a dominant trader between Asia and Europe. It had its own navy and currency, and established its own colonies, called trading posts. It was also the first company to issue bonds. In the beginning, investors from 6 business chambers, combers, provided capital for the business. Let's use these investments as key value pairs. When listing 7.20 is compiled, it produces an executable that generates the following output. Section 7.7.11. Adding a database index to Action KV version 2.0. Databases and file systems are much larger pieces of software than single files. There is a large design space involved with storage and retrieval systems, which is why new ones are always being developed. Common to all those systems, however, is a component that is the real smarts behind the database. Built in Section 7.5.2, Action KV version 1 contains a major issue that prevents it from having a decent startup time. Every time it's run, it needs to rebuild its index of where keys are stored. Let's add the ability for Action KV to store its own data that indexes within the same file that's used to store its application data. It will be easier than it sounds. No changes to libActionKV are necessary, and the front-end code only requires minor additions. The project folder now has a new structure with an extra file, shown in the following listing. The project's cargo.toml file adds some new dependencies along with a second bin surrounded by double square brackets entry, as the last 3 lines of the following listing show. The source for this listing is in ch7/ch7-actionkv2/cargo.toml. When a key is accessed within the get operation, to find its location on disk, we first need to load the index from disk and convert it to its in-memory form. The following listing is an excerpt from listing 7.24. The on-disk implementation of Action KV includes a hidden index_key value that allows it to quickly access other records in the file. The following listing shows a key value store that persists its index data between runs. The source for this listing is in ch7/ch7-akv2/src/akv_disk.rs. Summary. Converting between in-memory data structures and raw byte streams to be stored in files or sent over the network is known as serialization and deserialization. In Rust, SERD is the most popular choice for these two tasks. Interacting with the file system almost always implies handling stdio result. .result is used for errors that are not part of the normal control flow. File system paths have their own types: std path path and std path path buff. While it adds to the learning burden, implementing these allows you to avoid common mistakes that occur by treating paths directly as strings. To mitigate the risk of data corruption during transit and storage, use checksums and parity bits. Using a library crate makes it easier to manage complex software projects. Libraries can be shared between projects, and you can make these more modular. There are two primary data structures for handling key-value pairs within the Rust standard library: hashmap and btree map. Use hashmap unless you know that you want to make use of the features offered by btree map. The CFG attribute and CFG exclamation point macro allow you to compile platform-specific code. To print to standard error, std_error, use the eprintln exclamation point macro. Its API is identical to the println exclamation point macro that is used to print to standard output, or stdout. The option type is used to indicate when values may be missing, such as asking for an item from an empty list. Chapter 8. Networking. This chapter covers implementing a networking stack, handling multiple error types within local scope, when to use trait objects, implementing state machines in Rust. This chapter describes how to make HTTP requests multiple times, stripping away a layer of abstraction each time. We'll start by using a user-friendly library, then boil that away until we're left with manipulating raw TCP packets. When we're finished, you'll be able to distinguish an IP address from a MAC address, and you'll learn why we went straight from IPv4 to IPv6. You'll also learn lots of Rust in this chapter, most of it related to advanced error handling techniques that become essential for incorporating upstream crates. Several pages are devoted to error handling. This includes a thorough introduction to trait objects. Networking is a difficult subject to cover in a single chapter. Each layer is a fractal of complexity. Networking experts will hopefully overlook my lack of depth in treating such a diverse topic. Figure 8.1 provides an overview of the big topics that the chapter covers. Some of the projects that we cover include implementing DNS resolution and generating standards-compliant MAC addresses, including multiple examples of generating HTTP requests. A bit of a role-playing game is added for light relief. Section 8.1. All of networking in 7 paragraphs. Rather than trying to learn the whole networking stack, let's focus on something that's of practical use. Most readers of this book will have encountered web programming. Most web programming involves interacting with some sort of framework. Let's look there. HTTP is the protocol that web frameworks understand. Learning more about HTTP enables us to extract the most performance out of our web frameworks. It can also help us to more easily diagnose any problems that occur. Figure 8.2 shows networking protocols for content delivery over the Internet. Networking is comprised of layers. If you're new to the field, don't be intimidated by a flood of acronyms. The most important thing to remember is that the lower levels are unaware of what is happening above them, and higher levels are agnostic to what's happening below them. Lower levels receive a stream of bytes and pass it on. Higher levels don't care how messages are sent, they just want them sent. Let's consider one example, HTTP. HTTP is known as an application-level protocol. Its job is to transport content like HTML, CSS, JavaScript, WebAssembly modules, images, video, and other formats. These formats often include other embedded formats via compression and encoding standards. HTTP itself often redundantly includes information provided by one of the layers below it, TCP. Between HTTP and TCP sits TLS. TLS, or Transport Layer Security, which has replaced SSL, Secure Sockets Layer, adds the S to HTTPS. TLS provides encrypted messaging over an unencrypted connection. TLS is implemented on top of TCP. TCP sits upon many other protocols. These go all the way down to specifying how voltages should be interpreted as zeros and ones. And yet, as complicated as this story is so far, it gets worse. These layers, as you have probably seen in your dealings with those as a computer user, bleed together like watercolor paint. HTML includes a mechanism to supplement or overwrite directives omitted or specified within HTTP. The meta tag's HTTP-equiv attribute. HTTP can make adjustments downward to TCP. The connection keep alive HTTP header instructs TCP to maintain its connection after this HTTP message has been received. These sorts of interactions occur all through the stack. Figure 8.2 provides one view of the networking stack. It is more complicated than most attempts, and even that complicated picture is highly simplified. Despite all that, we're going to try to implement as many layers as possible within a single chapter. By the end of it, you will be sending HTTP requests with a virtual networking device and a minimal TCP implementation that you created yourself, using a DNS resolver that you also created yourself. Section 8.2. Generating an HTTP GET request with request. Our first implementation will be with a high-level library that is focused on HTTP. We'll use the request library because its focus is primarily on making it easy for Rust programmers to create an HTTP request. Although it's the shortest, the request implementation is the most feature complete. As well as being able to correctly interpret HTTP headers, it also handles cases like content redirects. Most importantly, it understands how to handle TLS properly. In addition to expanding networking capabilities, request also validates the content's encoding and ensures that it is sent to your application as a valid string. None of our lower-level implementations do any of that. The following shows the project structure for listing 8.2. The following listing shows the metadata for listing 8.2. The source code for this listing is in this file. The following listing illustrates how to make an HTTP request with the request library. You'll find the source code in this file. If you've ever done any web programming, listing 8.2 should be straightforward. Request GET issues an HTTP GET request to the URL represented by URL. The response variable holds a struct representing the server's response. The response.text method returns a result that provides access to the HTTP body after validating that the contents are a legal string. One question though, what on earth is the error side of the result return type box of din std error? This is an example of a trait object that enables Rust to support polymorphism at runtime. Trait objects are proxies for concrete types. The syntax box of din std error means a box, a pointer, to any type that implements std errors. Using a library that knows about HTTP allows our programs to omit many details. For example, knowing when to close the connection. HTTP has rules for telling each of the parties when the connection ends. This isn't available to us when manually making requests. Instead, we keep the connection open for as long as possible and hope that the server will close. Converting the byte stream to content. Rules for translating the message body from U8 surrounded by square brackets to string, perhaps an image, video, or some other content, are handled as part of the protocol. This can be tedious to handle manually, as HTTP allows content to be compressed into several methods and encoded into several plain text formats. Inserting or omitting port numbers. HTTP defaults to port 80. A library that is tailored for HTTP, such as request, allows you to omit port numbers. When we're building requests by hand with generic TCP crates, however, we'll need to be explicit. Resolving the IP addresses. The TCP protocol doesn't actually know about domain names like www.rustinaction.com, for example. The library resolves the IP address for www.rustinaction.com on our behalf. Section 8.3. Trait Objects. This section describes trait objects in detail. You will also develop the world's next best-selling fantasy role-playing game, the RPG Project. If you would like to focus on networking, feel free to skip ahead to Section 8.4. There is a reasonable amount of jargon in the next several paragraphs. Brace yourself. You'll do fine. Let's start by introducing trait objects by what they achieve and what they do, rather than focusing on what they are. Section 8.3.1. What do trait objects enable? While trait objects have several uses, they are immediately helpful by allowing you to create containers of multiple types. Although players of our role-playing game can choose different races, and each race is defined in its own struct, you want to treat those as a single type. A vec of T won't work here because we can't easily have types T, U, and V wedged into vec of T without introducing some type of wrapper object. Section 8.3.2. What is a trait object? Trait objects add a form of polymorphism, the ability to share an interface between types, to Rust via dynamic dispatch. Trait objects are similar to generic objects. Generics offer polymorphism via static dispatch. Choosing between generics and type objects typically involves a trade-off between disk space and time. Generics use more disk space with faster runtimes. Trait objects use less disk space but incur a small runtime overhead caused by pointer interaction. Trait objects are dynamically sized types, which means these are always seen in the wild behind a pointer. Trait objects appear in three forms: ampersand dyn trait,